After we have learned about the basic algebra of vector spaces in the previous chapter, this chapter will turn the attention to the geometry of vector spaces. So what's this all about? The geometry of vector spaces is about the definition of norms and inner products on vector spaces and about what you can do with these. Starting again with familiar vector spaces, such as Rn or Cn, we already have an intuitive understanding of what we mean by a norm and an inner product. On these vector spaces, the existence of a norm and an inner product seems almost automatic. However, this is not true for every abstract vector space. So there are vector spaces that do not have a norm nor an inner product defined on it. And these are called general vector spaces. If there's a norm defined on V, but no inner product, then the space is called a normed space. And similarly, if there's an inner product defined on V, then the space is called an inner product space. In fact, as we shall see, on an inner product space, there's also always a norm defined, which is induced by the inner product. So if we draw a little diagram of the set of all vector spaces, we have that the set of normed spaces is a subset of the set of all vector spaces. So a normed space is a special case of a vector space. And then an inner product space is again a special case of a normed space. Let's begin with the formal definition of a norm. So let V be a vector space. A norm on V is a function that's written with these double vertical lines that maps from the vector space into the set of real numbers such that the following three properties are satisfied. For any two vectors, x1 and x2, in the vector space, and any scalar alpha in the field, the following holds. First, positive definiteness, so the norm of any vector must be greater than or equal to 0, and the norm is 0 only if the vector itself is the 0 vector. Second, we must have absolute homogeneity, which means that if I take the norm of a product of a vector with a scalar, then this must be equal to the norm of the vector times the absolute value of the scalar. And third, we must have the triangle inequality, which states that the norm of the sum of any two vectors must always be less than or equal to the sum of the individual norms of these two vectors. And as already mentioned, the combination of a vector space with a norm is called a normed space. Next, on any normed space, it's possible to define an open ball, or simply a ball that's denoted like this, which is characterized by a radius, which is a positive real number, and a center, which is a vector in the vector space. And then the ball is defined as the set of all vectors y in V, such that the norm of the difference between y and x is less than the radius r. Of particular importance is the unit ball, which is a ball around the 0 vector with radius 1. Let's look at some important examples of norms. First, on the finite dimensional spaces Rn or Cn, some norms which are well known to all of us. First, the one norm, which is also known as the Manhattan norm, and it's defined simply as the sum over all elements of the vector x in absolute value. The two norm, or Euclidean norm, is defined as the sum of all the elements of the vector x squared, and then we take the square root of the sum. More generally, we can define the p-norm for any positive real number p that's greater than or equal to 1, and it's given as the sum over all the elements of the vector x to the power p, and then we take the pth root of the sum. And finally, the infinity norm or supremum norm, which is simply defined as the maximum over all absolute values of the elements of x. In an analogous way, we can define norms on sequence spaces and on function spaces. So for sequence spaces, we just consider the sequences as vectors of infinite length, and correspondingly the sum in the norm definitions goes from 1 to infinity. And for the supremum norm, we can keep the same definition as for finite vectors. For function spaces, we can also proceed in a similar way. So the one norm of a function that's defined on the interval from a to b is given as the integral from a to b of the absolute value of the function dt. And in the case of the two norm, it's the absolute value of the function squared dt, and then we take the square root. For the p norm, it's the absolute value of the function to the power p, and then taking the pth root of the integral. And for the infinity norm, we simply have the supremum of the function f of t in the interval from a to b. Note that this list of norms is by no means exhaustive, and we will actually get to know several more norms, for example operator norms, later in this course. Remember that we have defined a normed space as a combination of a vector space, a field, and a norm. So strictly speaking, these three normed spaces represent different normed spaces, even though the vector spaces and the fields are the same in each case. That being said, as long as we're dealing with finite dimensional spaces, so this n here is a finite number, then these three norms actually have very similar properties, and that's what we're going to look at next. In fact, as we shall see shortly, the three norms on Rn are what's called equivalent norms. And equivalent norms are defined in definition 5.3. So let V be a vector space. Two norms that we denote here generically with a norm A and a norm B on the same vector space V are called equivalent if there exist two constant real numbers that we call alpha and beta, such that for any vector x, the A norm is bounded by alpha times the B norm, and the B norm is bounded by beta times the A norm. Mathematically speaking, the equivalence of two norms is of great importance, because what this means in mathematical terminology is that the two norms induce the same topology on the vector space. And why is that important? That's important because the topology determines whether sequences of vectors in the vector space do or do not converge. That's obviously a very important property that we're going to take a closer look in the next few slides. Before we do, here's a little proposition with the number 5.4, which states that on a finite dimensional vector space, such as Rn or Cn, all norms are equivalent, which means that it's kind of convenient to work with spaces such as Rn or Cn. The proof of proposition 5.4 will be part of the next exercise sheet. So let's continue by looking at what it means for a sequence of vectors to converge. For this we have definition 5.5. What's important is that we need a normed space, so there cannot be any convergence without the definition of a norm on a vector space. What we consider is an infinite sequence of vectors xk in the vector space V. So here x1, x2, x3, and so on, they're all vectors. So these are not the elements of x, but each of them is now a vector. And the sequence is said to converge to some vector x bar in the vector space if the following condition is satisfied. For every given epsilon greater than 0, we must be able to find an n in the natural numbers such that the norm of the difference between x bar and xk is less than epsilon for all numbers k greater than n. Let's do a quick illustration of this definition. So suppose we're in R2 and we have some sequence of vectors in R2 and we want to know whether the sequence converges to a vector x bar in R2. Then the condition that must be satisfied for convergence reads as follows. For every possible value of epsilon greater than 0 that's given to us, we must be able to provide a natural number n such that the sequence stays inside an epsilon ball around x bar for all k greater than n. So in this particular example, suppose the green circle represents an epsilon ball around x bar for a particular value of epsilon, and the sequence of vectors enters the ball with the element x8, but it leaves the ball again and then re-enters the ball with x12, and then suppose the sequence stays inside the ball indefinitely. So in this case, our n would be equal to 11 because the remainder of the sequence is inside the epsilon ball for all k greater than 11. So starting with x12, x13, and so on. Now, according to the definition, we must be able to provide such an n for every choice of the value of epsilon. Of course, the smaller epsilon will be, usually the higher will be the number n. Now, if we're able to provide a number n for every possible value of epsilon that's given to us, and the sequence hence converges to x bar in the vector space, then x bar is also called the limit of the sequence. And we denote the convergence with the usual limit notation, so limit k to infinity of the sequence of vectors xk equals to the vector x bar. Two remarks about this definition. First, as mentioned before, the notion of convergence is fundamentally tied to the existence of a norm. So convergence is not defined for a general vector space that does not have a norm. Second, it's fairly easy to verify that if two norms are equivalent, then a sequence of vectors either converges under both norms or under neither of them. And this is recommended as a small exercise. Definition 5.6 is now about so-called Cauchy sequences. So again, let V be a normed space and xk denote a sequence of vectors in the vector space V. The sequence is called a Cauchy sequence if the following property is satisfied. For any positive value of epsilon that's given to us, there must exist a natural number n such that the norm of the difference between any two vectors xk and xi of the sequence is less than epsilon whenever the indices of the two vectors k and I are both greater than n. This raises the obvious question about the relationship of a Cauchy sequence and a convergent sequence. So we start with proposition 5.7, which states that every convergent sequence is also a Cauchy sequence. This is a very fundamental proposition that you may have seen before in your undergraduate math class. We will prove it here in order to get a little more familiar with the concepts of convergence and Cauchy sequences. So what has to be shown is the following. Let xk be any convergent sequence in the vector space V with some limit x bar in V. We must show that xk is also a Cauchy sequence. In other words, by the very definition of a Cauchy sequence, what we need to show is that for any given value of epsilon greater than 0, we must be able to show that there exists a natural number n such that the norm of the difference between two elements of the sequence xk and xi is less than epsilon whenever the indices k and I are greater than the natural number n. What's given is that the sequence xk is convergent, so by the very definition of convergence, for a given value of epsilon half greater than 0, there must exist a natural number m such that the norm of the difference between xk and the limit of the sequence x bar is less than epsilon half whenever k is greater than m, and the same thing obviously holds for xi. Now remember that we must provide a natural number n such that this condition is satisfied, and now what we do is we provide this n and set it equal to the number m from the convergence up here, and we observe the following. First, we look at the norm of the difference between xk and xi, and we subtract and we add the limit of the sequence x bar. Now we can associate these two terms in brackets and these two terms in brackets, and then we apply the triangle inequality for the sum of these two vectors, which gives us that this norm here must be less than or equal to the norm of xk minus x bar plus the norm of xi minus x bar. Notice that by our convergence assumption, this first term here is less than epsilon half, and also the second term is less than epsilon half whenever k and I are greater than n, because we have defined n equal to m. The two terms epsilon half plus epsilon half of course add up to epsilon, and hence reading the entire statement from left to right yields exactly the desired result. Now, what about the converse of proposition 5.7? It's an important fact that the converse of proposition 5.7 is not true for all vector spaces. In other words, it's not necessarily the case that every Cauchy sequence is also a convergent sequence on every vector space. Instead, every Cauchy sequence always converges to some limit x bar, but this limit x bar is not necessarily always an element of the vector space V. From your undergraduate math or even high school math, you know why this is not necessarily the case. So the following is a simple counterexample. Consider the one-dimensional vector space Q, which, remember, this is the set of all rational numbers, over the field Q and together with the absolute value as the norm. And then consider the sequence of vectors 3, 3.1, 3.14, 3.141, 3.1415, and so on. You can see where this is going. These are the increasing number of digits of the number pi. As it can easily be seen, the sequence is a Cauchy sequence, and moreover, the sequence converges to the number pi. However, pi is not an element of the rational numbers. Hence, we found a sequence that's a Cauchy sequence on the vector space Q, but does not converge to an element of the vector space. On this slide, we'll look at a few properties of Cauchy sequences which come in handy when working on some more complicated proofs. The first one is stated in proposition 5.8, namely every Cauchy sequence in a normed space is bounded, meaning that there exists a vector x tilde in V and a real number r such that the norm of xk minus x tilde is less than r for all k in n. You will prove this proposition as part of exercise sheet 4. For the next result, we need the definition of a subsequence. So let xk, where the index k runs in the natural numbers, be a sequence and let S be an infinite subset of the natural numbers, then xk, where k runs in the index set S, is called a subsequence of the sequence xk. Let's also illustrate this definition with some examples. We start from the sequence xk, where the index k runs in the natural numbers. So this is equal to the set x1, x2, x3, and so on. A possible subsequence, for instance, could be constructed by selecting only those vectors with odd indices, so x1, x3, x5, x7, and so on. Another possible subsequence would be to select only the vectors with even indices, so x2, x4, x6, x8, and so on. Or another possibility would be to select the vectors with prime indices, so x2, x3, x5, x7, and so on. And that works because the set of prime numbers is infinite. So basically, a subsequence can be defined for any infinite subset of the natural numbers. With this definition of a subsequence, we have the following result that is used quite frequently in other proofs. Namely, if a Cauchy sequence in a normed space has a convergent subsequence, then it is itself convergent. So what this tells us is that if we want to show that a given Cauchy sequence is convergent, it suffices to find a subsequence of the Cauchy sequence that is convergent, and then this will automatically imply that the entire Cauchy sequence is convergent. Now for the proof of proposition 510, we first assume that x bar is the limit of the convergent subsequence. And of course, what we will show is that the entire Cauchy sequence converges to that limit. To this end, we must verify the conditions of definition 5.5 for the convergence of a sequence. So pick any value of epsilon greater than 0. Since the full sequence xk is a Cauchy sequence, there exists a natural number n1 such that the norm of the difference between xk and xi is less than epsilon half for all indices k and I greater than n1. Moreover, since the subsequence xk is convergent, there exists another natural number n2 such that the norm of the difference between the limit x bar and the elements of the subsequence xk is less than epsilon half for all indices k in S with k greater than n2. Now we can define n as an index in the set S that satisfies that n is bigger than n1 and also n is bigger than n2. Then for any natural number k with k greater than n, it follows that the norm of x bar minus xk can also be written by subtracting and adding xn inside the norm, and then we can associate again these two vectors and these two vectors and apply the triangle inequality, which yields that this norm is less than or equal to the norm of x bar minus xn plus the norm of xn minus xk. Now we can bound these terms individually. The first one is less than epsilon half because of this condition, and the second one is less than epsilon half because of this condition. Now, when we add up the two epsilon halves on the right hand side to epsilon and we read the entire statement from left to right, we get exactly the condition that we need, namely the norm of x bar minus xk is less than epsilon for all natural numbers k that satisfy k is greater than n. So this means exactly that the Cauchy sequence converges to the limit x bar. So why is all this business with the Cauchy sequences so important? The reason is that Cauchy sequences lead to the fundamental concept of the completeness of a vector space. And that's what's stated in definition 5.11. A normed space is called complete if every Cauchy sequence in the space converges to an element of the vector space. In other words, if the converse of proposition 5.7 holds for this vector space. Again, completeness is a very important property of a vector space that we will make heavy use of in the rest of this course. Now, a few more remarks about completeness. A normed space that is complete is also called a Banach space. So whenever you see the term Banach space in the literature, this means that we're dealing with a normed space which is complete. As before, our well-known vector spaces Rn and Cn have all the nice properties, so in particular they are Banach spaces. On the other hand, a normed space that is not complete and hence not a Banach space is the space Qn. As we go along in this course, we will see more examples of Banach spaces and non-Banach spaces.